Vertical stretches and shrinks of absolute value functions. Stretching the graph of a function f of x vertically away from the x-axis is given by a times the function f of x, provided that a is greater than 1. When this happens, f of x stretches away from the x-axis by that factor of a. So notice we're going from the red parent function f of x to g of x, which is 2 times f of x. So we're going from negative 1, 1 to negative 1, 2. And we're going from negative 2, 2 to negative 2, 4. The origin is still the same because that lies on the x-axis. But the other points that are not on the x-axis in the original parent function are being stretched further away from the x-axis. And they're doing that, in this case, by a factor of 2. Now let's discuss vertical shrinks. When vertically shrinking a graph of f of x, you're shrinking it vertically towards the x-axis, and that's given by a times f of x, provided that our a value is between 0 and 1. This makes our function f of x shrink towards the x-axis by that factor of a. If we begin with our parent function f of x is equal to the absolute value of x, we can see here that it goes through 1, 1, 2, 2, negative 1, 1, negative 2, 2. And when we have h of x, which is equal to 5/10 or 1/2 times f of x, we're taking each of our y coordinates and shrinking them down towards the x-axis by this factor of 1/2. So for example, we go from 2, 2 to 2, 1. We go from 1, 1 to 1, 1/2. Since the point that's at the origin lies on the x-axis, it does not move as a result of this vertical shrink. However, all of the other points that are not initially on the x-axis vertically shrink towards the x-axis by this factor of 0.5 or 5/10 or 1/2. Now let's try an example problem. We're going to use function of x was equal to the absolute value of x minus 2 for each of the problems down below. We're going to first write the ruler formula for the new function after the transformation that we're provided. Then we're going to graph the transformed function in the coordinate plane shown here to the right. So the first one that we have is 3 times f of x. So that is going to equal 3 times, we're going to take f of x, which is the absolute value of x minus 2, and we're going to substitute it in for f of x. So absolute value of x, and then minus 2. And then we're going to distribute this 3 through to both terms, and that will give us a final equation. We could write it as y equals, it'll be 3 times the absolute value of x minus 6. So therefore, one of our points that we're going to graph is the point 0, negative 6. And then instead of having the initial slope of positive 1 and negative 1, we're now going to have a slope of positive 3 and negative 3. So this is 3 times f of x, this red graph that we have. Now let's look at question B here, 5 times f of x. So for 5 times f of x, that's going to equal 5 times the absolute value of x minus 2. Again, remember, because this is in parentheses, we need to distribute through. So we're going to have 5 times the absolute value of x minus 10 as our equation. So it goes through the point 0, negative 10, and then instead of having a slope of 1, as the initial parent function does, this one's going to have a slope of positive 5 and then negative 5. So 1, 2, 3, 4, 5 right here. 1, 2, 3, 4, 5 right here. 1, 2, 3, 4, 5 right here. Now we'll do the same thing going the other way. So up 5 over 1 up 5 over 1, 3, 4, 5. Okay. So here on the right-hand side, we have that slope of 5. But then over here, the slope is negative 5 when you go from left to right. So this is for 5 times f of x is in blue. Now let's look at the last problem that we have, which is 1/2 times f of x. So that's going to equal 1/2 times the entire f of x function, which is the absolute value of x, minus 2. And remember, we have to distribute the 1/2 through to both terms. So we're going to have y equals 1/2 times the absolute value of x minus half of 2 is 1. So then our y-intercept is going to be at -1, and our vertex for that matter. And then instead of going up 1 and over 1, we're going to go up 1/2 and over 1, or you could go up 1 and over 2. So then if we connect all of our points, we end up getting this function. So this is 1/2 times f of x for this graph. And here are the solutions to the 3 examples that we just worked out, and they do match the solutions that we found. Again, notice that any point that was not already on the x-axis ended up getting pulled vertically away from the x-axis when the coefficient or the factor that we were multiplying by was greater than 1. So notice 5 times our function, it stretched it way out here by that factor of 5. And 3, again, it stretched it both up and down by that factor of 5. Now because in part C we had the factor of 1/2, it actually shrunk it towards the x-axis. Here's another example with vertical stretches and shrinks. We're going to let our initial function f of x be equal to the negative absolute value of the quantity x minus 2 and then plus 4. Its graph is displayed here to the right. Notice that this function is actually written in vertex form, where we have h is 2 and k is 4. So we have 2, 4 as that initial vertex of our absolute value function. And it's negative, so it's opening downward. So now let's take our function f of x and determine what g of x is by multiplying f of x by 2. So g of x is going to be equal to 2 times f of x, so that's negative absolute value of x minus 2 plus 4. And then remember, we have to take this 2 and distribute it through here. And remember, there's this hidden -1 here. And we're also going to multiply it by 4. So therefore, g of x is going to be equal to -2 times the absolute value of x minus 2, and then plus 8. This tells us that our h value and k value for our vertex are going to be 2, 8. Okay, 2, 8 is way up here. And actually this kind of makes sense because we're taking our function values and multiplying them by 2, and 2 times 4 gives us 8. All right, so then now instead of having a slope of +1 here and -1 here, we're now going to have a slope of +2. So these are going to be following the path of our function, and then we'll have a slope of -2 on this side. So our graph, when we connect all of these points, is going to look like this. And we're going to label 3 points like the directions say. So we have 2, 8, and then I'll label this point here 4, 4, and that it corresponds to the y-intercept is 0, 4. And here are the solutions to our example problem, and they do indeed match the solutions that we found. Notice again that each point that was not already on the x-axis was vertically stretched upward by a factor of 2. So we went from 0, 2 to 0, 4. We went from 5, 1 to 5, 2. We went from 2, 4 to 2, 8. And then the formula for g of x is -2 times the absolute value of the quantity x minus 2, and then plus 8. And what we have been learning about and seeing in our graphs is that stretching or shrinking the graph of f of x vertically away from or towards the x-axis is given by a times the function f of x. If a is greater than 1, then f of x stretches away from the x-axis by the factor of a. And if a is between 0 and 1, then f of x shrinks towards the x-axis by that factor of a. So here we have f of x given in red here, and we are stretching it away from the x-axis to get to g. Notice we went double the amount of spaces, or the same amount of spaces from the x-axis to the initial point of f, and then from f to the next point in g. Similarly here, we go up 1, 2, 3, 4 to get to this point, and if we go up to that same point in g, it's going to be up at 8, 2 times 4. So we can start at 4 and count another 4 up. 1, 2, 3, 4. It'll be right up here, if you can visually picture g extending up. It also follows that f of 1 is equal to 2, and g of 1 is equal to 2 times f of 1, or 2 times 2, which is 4. So the point 1, 2 stretches away from the x-axis to the point 1, 4. Now if we have a factor that's between 0 and 1, it shrinks towards the x-axis. So in our example that we have here, h of x is equal to 1/2 times f of x. If we notice at the x-coordinate of 3, 1, 2, 3, we have a y-coordinate of 4 in f, and then h of 3 is going to be 1/2 times that 4, or 2. It's going to shrink towards the x-axis by that factor. So we're shrinking that 0.34 towards the x-axis to the 0.32. For this point at 1, 2, it shrinks down to be 1, 1 from f to h.